Well, one of the things I keep saying to people is I believe math should be taught with as many concrete examples as you can, especially algebra in the beginning. The more we can tie it to concrete experiences, the easier it will be for our students to make that step to formal abstract reasoning. So I'm a big proponent of, when you can, and just about always you can, start with a concrete experience and base the algebra on that concrete experience. I'm just going to show you a little tiny setup we have that we use in our beginning algebra classes just to try and tie what they are studying to real events. I believe that's crucial. Take a look at this little short piece. Well, this experiment couldn't be any simpler. All we do is, this is a motorized cart, and of course, the way my day's been going, the batteries don't work in it. I need to go get new batteries. I looked all around, couldn't find them. So what we do basically is, we just run this cart down through between these meter sticks, and at each second, we write down where it's at. And with it going at a constant speed, and that's the crucial thing here, with it going at a constant speed, it just keeps moving right along, and we can just mark where it's at. That's the basic experiment. Okay, I've written on the board just some results that we get from this very simple experiment. But what I want them to see is this data actually comes from some specific experiment that they do. So we're just going to plot these on a graph here. And we have 0, 0. We have 1, 10. 2, 21. I'm trying to do the best I can here. 3, 31. And 4, 41. And hopefully what we see is, this makes a very nice straight line. And the question is, well, what good is a graph? Well, a graph, especially when we get nice linear relationships, we can develop an equation from that graph, and then we can stop basically doing the experiment because we can use the equation to answer any question that we might have, such as, I wonder where the cart would be at the end of 6 seconds. Or, I wonder where the cart would be at the end of 2.5 seconds. The equation can give us that information. We don't have to go back and do the experiment. So, how do we do that? Well, we start with our old tried and true equation of a straight line is y equals mx plus b. And we just put into the y and the x what we plotted. And the y-axis here, this is centimeters. That's what is on this graph, this axis. And what's on this axis is time. So I'm just going to say y, which is, can I say distance? I'll use d for distance, equals m, which stands for the slope of the line, times x, and I'll just use t for time, plus b, which is where it crosses the y-axis. Now this one has a nice, neat, crossing the y-axis right at 0. When x is 0, y is 0, so the y-intercept, the plus b, is just 0, so this equation comes down to just this. Distance equals slope of the line times t. Now, so many times I ask students, what does the slope of this experiment stand for? And they look at me like, you mean it could be a real thing? The slope could actually be something? I always thought it was just changing y or changing x, and that's all it is. Well, that's where I like to say, let's not divorce it from reality. This is actually distance here, time here, and when we plot the slope, we will get distance over time, which is a crucial concept of velocity. And they see that develop right from the graph. So I'm just going to take this point right here, and this point right here, and figure our slope. Remember, changing y over changing x. Our change in x is probably the simplest. It's 4 minus 0, so x changed 4 units. y went from 41 to 0, so y changed 41 units. So our slope is going to be change in y, which is 41, over change in x, which is 10, times t. Now we could reduce that down to 4.1t. And this is a very important concept of velocity. This is how fast that card is actually going. And our labels would be, let me write it up here, 4.1 meters per second times time. Because the label for distance, I'm sorry, it wouldn't be meters, it would be, it's good to go back and check. Let me erase this. This would be 4.1 centimeters per second, and that would be an actual real thing. That's the velocity. We could actually write it this way also. Distance would equal velocity times time, and for this particular experiment we talked about, this would be our velocity. What is my important point here? My important point here is this. When we're teaching math, let's start from concrete, real experiences, and then we can develop the abstract formal reasoning. If we try and do it the other way around, many students will be left in the dust. I hope that helps, and I hope you have a great day. Bye-bye.